I just hit record now. So we will be doing this one next. And I have a document with around 6 extra questions, which is exactly the same as your book anyway. But of course, there is always an extra applied force on this thing. But anyway, let me just, this is the one we're going to solve before we move on to the next section. Nevertheless, so it says, figure 5 shows a drum being pulled along a horizontal plane by a 1.5 kilonewton force. Shows a cable drum being pulled along a horizontal plane by 1.5 kilonewton force applied to the cable. Right, so there's a cable there. The cable is maintained horizontal. The mass of the drum is 1,200. The radius of 400. The radius of gyration of 400 millimeters. Determine the drum's true linear. Yes.
I cannot see the screen. Is it
need to refresh
only myself?
Yeah, so you just have to refresh. In case it happens. Determine the drum's true linear and angular accelerations if mu between the flanges and the surface on which it moves is 0.1. If it starts from rest, determine the kinetic energy gain by the drum and it has rolled for 10 seconds. So you can see it's essentially normally the same kind of setup as all the other previous problems. But now, let's open my book here. Let's get this. Right. So, like I said, again, so the first stage of our problem is to check whether it's rolling or slipping. Okay, just want to zoom out here. Okay, so again, we do exactly the same as before. In this case, if you're looking at the force from the body, so this is being pulled this way. So therefore, we experience an angular acceleration going that way. Alpha, our frictional torque will always be, our inertial torque, sorry, will always be there. And of course, we have F mu also going that way. That's the forces on the body. Okay, so we start again the same. A equals R alpha. We assume no slip. Always. We assume it's only rolling. And once we do this, A is equal to, so here in this case, we have to use a bigger radius, 0.5 alpha. That's the main body's movement. Okay. And of course, this will become, it's a half, so that's 2. So the angular acceleration is 2 times the linear acceleration, right? Okay, so we've got that. What's the next step? Like I said, horizontal forces. Fx equals 0. Mr. Zam, give me the horizontal forces on this thing. Now, I want it in equation form. Just give me a second. What are the horizontal forces? Oh, and of course, I forgot another force, which is Fz. All right, okay. So what's my horizontal force acting on this body? Almost the silver. Makes them Zambia easier. So what's the forces? Thank you.
Is Fz plus Fu
Yes. Fantastic.
equals to 1.5.
Beautiful, Chief. Thank you very much. Again, remember what we're going to be dealing with is making it in terms of mass and acceleration. So M, this will be over here. So I'll say, what is this? Fz is, what's the weight again? 1,200. Okay. Plus F mu we're keeping as before. and that equals 1.5 or 1,500, right? Newtons. Got equation 2. That is fairly simple. So what I'm just illustrating for you now, because you guys are not familiar with when you have an additional force applied here, right? So I'm just showing you that. Once you can do that, you can essentially solve all of them. Well, you see what I mean. So of course now we're taking moments about the center. I'll say moments about center. Okay. So I'll start with the 1.5 force, and at the center it's 1.5 times this radius now, so that's 600, and that's going anti-clockwise, so it's 1.5 kilonewtons times the radius of this part of the drum over here, so that's 0.6, so not 0.5. So 0.3 is the radius, the diameter is 0.6. If mu is on the outside, obviously, and that's clockwise to that point, so that will be F mu times 0.5 on this end. It's on the clockwise side. And of course, we have our inertial torque, which is also going anti-clockwise, which is on this end over here. So that's plus I alpha, right? And of course, the job here is to make this in terms of A. So my I is mass times the radius of gyration squared, and our mass is 1,200 times the radius of gyration is 0.4. And if you get that, you should get a value of 192 kilogram meter squared. Don't worry, you'll be setting everything up now. Of course, our angular acceleration is equal to 2 times A. So we have that over here. And of course, we want this to be in a matrix form. It's a equation. Okay. Yeah, you could say FZ is straight through the center. Yeah. Yes, we can assume that. Yeah. But I think it's a good way of assuming that. Yeah. It's not assume it's the inertial force. So yeah, you're never going to have a moment on that. Okay, so here we have F mu 0.5 F mu minus 192 times 2. Not smart enough to do that. So then we have 384. I hope I didn't miss anything here. 384A, and that'll be equal to 1.5 times 3 times 0.3, which is 450. Hoping that I'm correct here. And now I want you guys to find what is F mu and what is my acceleration. And so now, see, they don't tell you here. They say determine the drum's true linear and angular velocity. So we first have to determine whether it will roll without slipping or roll with slipping. And you understand why I'm deliberately giving you this one. So anyway, I'm giving you guys 3 minutes to quickly solve that. You can pull up that matrix and solve this. Oops, sorry. So can someone please get my F, mu, and A values and determine whether it will roll without slipping or roll and slip? Brent, Mr. Kiefer? Mr. Mzam? Do you guys, are you guys lost with this particular section, or Melissa, Mr. Wheeler?
On my side, I'm not using matrix because I don't have that calculator. So I'm just substituting.
My sincere apologies.
That's cool.
Okay. So let's get those values, guys. I mean, I want you guys to tell me the values and whether it's rolling or slipping. It's very important.
For the acceleration, I got 0.457. Is that correct?
Nope. Are you sure? 4.5. Come on, guys, man.
0, okay, it's not 0.
My acceleration is 0.35.
0.3, yes?
0.305.
Fantastic. Okay, and your friction force? Let's see what
It's
I want.
1134.146.
Beautiful, beautiful. I'm expecting a distinction on this, man. Let's see, 1134. Hey. Keep it neat here. And acceleration is 0.30, yeah, 48708, just meters per second squared. So my question is, what do we do now? We have to find F mu max, Mr. Mzam, and F mu max is mu times N. And can someone get me that value as well? So it's 0.1. Of course, our normal force will be equal to the weight in this particular case, which is 1,200 times 9.81. What is the answer? I want to hear what if is rolling or slipping from you guys.
I think it will roll and slip. No, say it will roll. It's rolling. So are you still there? I can't hear your audio, sir.
Mr. Scope.
Okay. Can you hear me now? I just hit the thing on the. Yes. Okay. Fantastic. Mr. Zam, fantastic. So our our maximum friction force is um what's it 1177.2. Comparing this value is that a question there? No. Comparing that value with this one. So this is less than that value, and if that is the case, it will only roll. And that is perfect. That's two marks. And like I said, if that is the case, so the actual angular acceleration is going to be 0.30488. And for us to find the angular acceleration, it's just going to be the angular acceleration divided by the radius. In that case, oh, sorry, did we find that relationship already? It's 2 times, sorry, it's 2 times. Forgive me. So it's 2 times that value. Okay, fantastic. Okay, so alpha is equal to 0.60976 radians per second squared. Can you see now we don't have to do any adjustments at all with our calculations. Now it's perfectly fine. So it's only when we find that a slip and roll, you're going to have to use our friction max and then recalculate on new values. So it'll roll perfectly. So the next part of the question says calculate, if it starts from rest, determine the kinetic energy gained by the drum when it has rolled for 10 seconds. Okay, so let's quickly do that. So I'll just do it over here. So of course we know kinetic energy is equal to half mass v squared plus half I omega squared. It's rolling and it's a translational and rotational motion. I'll take a common factors here. This is like the easy way to do it. Then we have v squared, and over here we're just going to have k squared, and here we're just going to have omega squared. I don't want to show you this before. So all we need to do is find our velocities. Just because we have the rate of gyration. So v equals u plus 80. From rest, our acceleration was 0. What is acceleration here again? 0.3 or something.
305.
5. So it's 10 seconds, right? Get that value and you can get omega in a similar fashion using angular acceleration. Okay. You see that I have a bit of a problem with that. Yeah, I don't know. I probably will. I guess. I don't know. I need to think about that. That's kind of mechanics 1. I just want to find out something as well. I'll see. Okay, anyway, so can we get this velocities quickly? Yeah. I haven't studied like in 5 years. Yeah. I'll think about it. I'll think about it. Just give me. So prepare the formula sheet without that. I'll see. We'll speak about it. We'll speak about it. Okay. So then omega would be now 0.607. I don't know what omega was. 0.6 or 976 times 10 seconds as well, just multiplying by 10, so it's 6,09756 radians per second. Okay, so plug and play that guy. Can you guys give me the total kinetic energy? So what I've showed you is two different ways here. Well, not two different situations where something will roll and slip or just completely roll. And yeah, like I said, if you can do, but anyway, just find the kinetic energy, then I'll close off this section of the work. Mr. Silver, what is the kinetic energy due to, well, the total kinetic energy? Okay, guys, you should get a value of around 9146.33 kilojoules. Are we happy about this? Do we all get this? All right. Guess no one's saying anything. Also, questions like these could arise, right? What was the distance traveled? What are the distance and revolutions experienced by the drum? Distance traveled and experienced by the drum. Questions like that could come up, you know, could V plus 2AS. You can exactly see how long the drum traveled in that particular time. For instance, the total amount of, alternatively, if you want to do the revolutions as well, 2 alpha S or 2 alpha theta. We can also find this, and we quickly just have a look at these values. So I'm just showing you there are those questions which can also come into play. So that'll be around 15 meters, 2366 meters, and the other one would be. So you mustn't forget your previous stuff you've learned in your previous level of mechanics. Everything is in there.
Check. Anyone hear me?
Yeah, we can hear you, Matthew. And that's 0.0976. So this is in radians. So I think so how do we go from revolutions to radians? From radians to revolutions?
Hello. Can anyone hear me?
We can hear you, Mr. Doyle.
I can't hear anyone. Can't hear anything.
So how do you go from radians to revolutions? Can you guys hear me?
Yes, sir, I can hear you.
Okay, fantastic. So how do we go from radians to
I just simply times by 57.3.
oh, lekker, 57.3.
Yeah,
So how do you get that 57.3?
that's 180 divided by pi.
Is that radians? Are you sure about that? Just that's to revolution. Well, that's to the degrees. I'm asking the amount of revolutions. There's a factor of 2 pi there.
Well, see, this is why I just remember 57.3. Because I just convert radius to degrees and then I divide by 360.
Yeah, you have to divide by 2 pi to get the
2
amount
pi,
of
yeah.
radians. Yeah. It's not. So you just divide that 30 odd. And of course, the reason why we look at the reason what we're trying to say here is that if the drum was initially at that point, it'll go once, twice, 3, 4, nearly 5 and stop. It spins that amount of times. That's what it is. 4,8552 revolutions. You'll pick this up also when you're dealing with brakes. Now there's some bonus questions. Obviously, you're required to know that. I mean, it's normally the case. So guys, I hope you guys have learned something here. I'd like to move on to the next part of the thing. Is there any questions regarding slipping and rolling conditions? When you receive a lot of practice, do not worry. And if you can do this, oh yes. Is there any questions? Just let me know if there's no questions so I can move on. I want to show you exactly how it's probably how hard it's going to be. It doesn't get any harder than this. So any questions?
Not right now, but I mean, like, if I'm busy working through your tutorials and stuff and I have a question, can I send you a message?
Of course, Mr. Solver.
Thank you.
I prefer, like, some people send messages like on Sunday and the weekend. Like, just you can see. The problem is I don't mind responding. There's something I have other things to do, so I don't want to let you hang. So preferably in the week, during work hours and stuff, or even just during the week is better than the weekend. So, and when I mean the week, I mean Monday to Thursday. It's Fridays, yeah, but you can send questions definitely. So would you please explain this question of a drum? I don't understand what you mean. I'm not with you. Zam, you can speak up and tell us. So one word with Zam to say something. Like I said, this is the hardest the question you can probably get. So you have an incline plane, you've got a force on it, and yeah, that's the hardest you can expect. And this question, like I said, goes around 15 to 20 marks in the paper, depending obviously. You'll see it in test 2 and you'll see it in the final. This kind of setup. Mr. Mzam, I'll give you 2 minutes and then I'm moving on.
So what were you asking on question 3? Oh, this question that you just asked.
No, I never asked anything. I asked, do you have any questions?
No, I'm saying the question that you just did.
What about?
Like, what were you asking for?
I mean, do you not do the example? I'm confused. So are you lost with the question I was asking for?
Yeah, this added question that you just did now.
Oh, sorry. So, what I was asking for is, what was the distance traveled and the revolutions experienced by the drum? So what I'm saying is that if this drum is obviously being pulled against this thing, so I'm asking how far did it move from here to here? That's the first one. That was like 15.236 meters. And the second one is how many times did it actually rotate in terms of revolutions? And so we've established it rotated 4,8552 revolutions. Are you with me, Mr. Zam?
Yes, sir, thank you.
Yeah, okay, sorted. No, I'm just saying, like, you know, those extra questions based on mechanics 1, you know, it was done for a reason in the previous thing. All right. Okay, so we can close this off. And I can go back to my slides now. And we can start on hoists. So clearly, I actually, obviously, there's no way we're going to finish all of what I had expected. I'm going to have to set up another lecture for hoists. But anyway, got 30 minutes left. Oh, wow. 20. Okay. So let's move on. So guys, this is the second application or the second thing. Like I said, there's normally 3, but we might probably just do 2. Oh, can you guys hear me? See, my mic was muted. So what I was explaining here is this is what a hoist is. And oh yeah, well, they can't hear me. I don't know what's happening there. Don't worry, Matthew. You can always just rewatch the lecture again. That should all be here. So we're going, like I said, with the hoist and haulages. And I just said a hoist is a device used for lifting or loading a load by means of a drum or lift wheel around which a rope or chain wraps. Right. So the lift wheel essentially is a normal drum, right? And it may be manually operated, electrically or pneumatically driven. It may use a chain, fiber, or wire rope as its lifting medium. So like I said, it's a wire rope very commonly or chain. So this is like a typical overhead crane. And this over here is a rope drum hoist. So you have these ropes around there and you've got this crane at the bottom to lift the actual thing. What I'm saying is this what we're doing now is particularly important. Because remember this one video you guys sent me, I think it was a crane, they were lifting some container, place it on a boat. But like if you're unsure of lifting a particular weight, I mean, besides checking the specs of the actual these guys, this is not part of test one. Please, man, please. I can't. How can I teach something for in the same week? You know, I mean, I would never do that. So this is not part of test one. Please check on the group. So yeah, and if you're all concerned of if you ever have to ensure that you want to lift something correctly, this approach which I'll be showing you is approach of guaranteeing that you will ensure that you're able to lift it. Of course, you know, in typical engineering applications, one will just clip it on and hope for the best. You can actually just check the specs of the machine. It'll exactly tell you how much kilograms it can weigh. But I mean, if you are trying to create something novel, the approach I'll show you today will greatly help you in deciding which motor maybe to use or I guess how to lift it. There's different ways of doing it. Anyway, the typical machines being used here. It says all three types of machine make use of a rope wound, a winding drum, and it's rotated by an applied torque, which of course is normally driven by an electric motor, induction motor. The rotating drum winds the rope to raise or pull the load. Okay, so a hoist is used to raise a load directly as in a boarding or loft. So that's what actually a hoist is like. The hoist drum uses the motor through a gearbox, of course, its transmission system to step down the speed and increase the available torque. That's very important because we were actually looking at that kind of stuff. Matthew's mic is unmuted. Oh, it's muted now. And then we've got a winch. So a winch is the same as a hoist. So instead of vertically be going now more of a horizontal thing, except that is used to haul, it's like I could say it's a haulage, a load horizontally, as when hauling a boat up a slipway. So that's a winch. So small winches can be operated by hand crank, large ones are usually motorized, obviously. What I also mentioned is that if the Egyptians and so the so-called aliens, they could have invented this technology and helped them build the pyramids much more faster than, well, as archaeology says or history says. Then of course a crane, this is a very common one, is used to raise loads vertically, where the loads to be raised at a height above the winding drum. That's interesting, eh? Between a hoist, winch, and crane, and it's normally by sheaves placed at the end of the crane boom. So that's just typical lifting machines. And of course, always to use the principles of some simple lifting machines. Got your pulley arrangements, those kinds. Especially learned in mechanics one, marine science one. Right. What I want to show you guys is I'll show you the basic examples, and what is to be expected of you is something like that. It looks like this. Alternatively, it looks like that. A motor, gearbox, the actual winch, you've got an idler drum in between. And of course, these are things which I have to go through. But anyway, So I'll just explain the generic principle. So how it works, and this is for hoists, which is essentially an accelerating system with linear and rotational motion, which I should actually call the chapter that. It's essentially it's the consolidation of D'Alembert's principle, and it'll just say like draw a free body diagram for each individual item, and I'll show you this approach obviously for each object that goes linear motion. Indicate on the free body diagram all the forces acting on the object as well as the direction of the linear acceleration. These things we've been doing. Then apply to the FBD the equation F equals MA, which is the elements principle. Obviously, we have to do that. We've touched on it a bit now with our rolling and slipping conditions. We do exactly the same thing with the torques on our FBD, and then we apply change in torque equals I times alpha, right? And they're saying the above picture allows us to set up in one equation for each connected object in accelerating systems. For example, if there are 4 objects, it is possible to set up 4 equations and then solve 4 unknowns. Fantastic. Also, additionally, since a linear acceleration of the point of the drum passing around the drum is related to the angular acceleration, we can make use of A equals R times alpha. And that is a very powerful equation which we'll be using the whole time throughout this particular chapter. So again, the first step is to break down each one. Second thing is look at all the linear stuff, sort that out, then go to the rotational stuff, or the torque, sort that out. We get a few equations. You might sit with a 2x2 or 3x3 matrix. It might happen or might not happen. And eventually we can solve all the knowns, and then yeah, you'll see. So another thing is important here, which I've just literally discovered last night, and I thought it'd be cool, is something called efficiency of a hoist, which is essentially the power developed by the motor, also the power used to hoist the load, which is normally the force times velocity. And of course, I'm going to show you this to you guys. And then we have to divide that by the power developed by the motor, which is torque times omega. And we have to specify after how long it is. We normally look at 1 second. So we can actually look at the hoist is, and if there are particular elements which is not that efficient, you can actually adjust maybe mass moments of inertia of those particular elements, and then you can actually increase the efficiency of the hoist to see how actually efficient the power from the motor is actually being easily transferable into yeah. So okay, so what I'm going to do now, I'm going to do 2 basic examples of applying this thing, and I'll do it on the slides. Okay. So the question is here, so suppose a drum with a mass moment of inertia of 80 kg/m², diameter that much, express a friction torque of so much. It's got a hanging piece of mass. More that acceleration or the mass piece descend, ignore the mass. So, like I said, what we can do, we normally look at all the linear counterparts, right? So what is this thing here? What acceleration will the mass piece descend? So we have a drum. So guys, it's a very basic example. So I'm going to explain this concept, right? And it's saying it's descending, so that we know that acceleration is going downwards, right? So there's a mass piece on here, 10 kilograms. Okay. Yeah. And now what you're looking at, what is A, right? So what acceleration is this going? So what happens is we start, as the question says, I'll do it on here, just forgive me. So a very basic thing. We look at all the linear parts, which is this. We know that on this body, we've got the tension of the rope, right? We've got mg going. And then, of course, if we're accelerating downwards, we've got F Z. Is that correct? You guys agree? Are we all there? Okay, you'll see how it works out. Yeah. This is like a building block to what we actually need to do. And then where am I now? So then we can set up a first equation, and that's going to look like this. It's mg plus I'll write it on top. Equals Fz plus T1. Of course, we don't know the first tension, but the mass is going to be 10 times 9,81. I'll say minus T1, and Fz is going to be 10 times A. This is what we're looking for. So we don't have T1 and we don't have A, right? Now, what we do now, like I said, like I mentioned in the previous slide, is that now we have to go to the second part of the thing, and we have to look now at the so-called drum over here, right? So the drum is turning this way, obviously. So the angular acceleration is going that way. We've got a frictional torque. I'll call him TF. Plus we have our inertial torque TZ. Plus we have this torque over here due to T1, right? So now how do we do that, right? So this is okay. We essentially applied F equals MA here. Sorry, sum of F equals MA. And you do exactly the same over here. Torque equals I alpha. So we're familiar with this, and I have to look at all the torques. So the first thing is we take T1, and T1 is going clockwise. T1 times 0.4. And of course, if that's going clockwise and these guys are all going anti-clockwise, that means we have negative the frictional torque, and we have negative I times A. So that we know that's 80 alpha equals 0. Alternatively, I can just bring it to the other side and make 80 times alpha. And of course, alpha is also, we know that alpha or A equals alpha R, and that is going to be now A over R, and that therefore this is going to be now A. Yeah, my eraser quickly. Here's my eraser. Okay. So this becomes now 80 times, I said A over R. A over R is, so 0.4. So we have T1 0.4 minus 20. That's going to be equal to 80 divided by 0.4 give us 200 a day. And excuse me, so we've got one equation here, we've got another equation over here, and I'll probably just duplicate this, just remove that. So we have two equations. Equation number one is 10 times 9,81 minus T1 equals MA, which was it 10 times A? Yep. And then we have the next one was 0.4 T1 minus 20 minus 20. That's a frictional torque that equals 200 A. And of course, this is simple. You can solve it with a 2x2 matrix again. And if you do that, the tension will come out to 96.1765 newtons, and your acceleration equals 0.1924 meters per second squared. So if you're looking at this value, it says you can see this value is less than your 9,81, and then that will mean that the tension of the rope is less than the value of mg for the mass piece, obviously. Sorry, it's an email. Okay, so I just hope I'm basically done with this part. I urge you to go over it. I will send you some notes based on hoists. Well, I think what will happen with hoists is that I'll probably have to prepare a recording of this. Alternatively, I will have to see you guys Monday, something around that, yeah. But what's going to happen is, just to close off now, is that you'll be looking at each system. You start over here, you move over here, you move over here, essentially move over here. So you will break up each individual thing. So it's, for me, I think it would be best to go over this with you guys in detail so that you guys have a complete understanding of hoists. Okay, so guys, I recommend watching this again, specifically obviously the whole lecture, and then it's just the start of hoists. The next example will be in a book if you want to study ahead, which I doubt you will. But yeah, anyway, I hope you guys learned something today, and I'll either see you next week Friday. Yeah, I will see you next week Friday. Definitely. Oh, not next week Tuesday. No, not next week Monday. Obviously, because due to the yeah, but I will see you guys next week Friday on the 30th of April. Anyway, guys, cheers for now and enjoy the rest of your day. Bye.
Thank you, sir.
Pleasure, man. Prepare for your test.